Okay, so I guess we'll go ahead and start this combined handout for chapters 3 and 10. They go together. Chapter 3 is a descriptive statistics topic, and that's why it's back in the beginning of the book. Chapter 10 is an inferential statistics topic, which is basically going to be a hypothesis test. But they go together, meaning the descriptive statistics you learn in chapter 3 become the subject of hypothesis tests in chapter 10. But they are covering the same ideas, and you can use the same examples. So it makes sense to do them together. What we're working on now are quantitative variables. But there's going to be two variables. So if you look at the example here, just looking at the numbers, there's a variable x and a variable y, and we're going to try and find out when one variable affects another. And affect is probably the wrong word, because we're not going to be doing experiments that determine cause and effect. But we want to find out when there's a relationship between two variables. The language is really tricky because we have to be really careful to use language that doesn't sound like cause and effect, and yet we still want to be able to say, hey, well, these variables are related in some way, but it may not be a causal relationship. Okay, so let me go ahead and let's read this example. It says, in this lesson, we look for rules that describe the relationship between two quantitative variables. Here comes. The FBI, ATF, and AAA compiled data for 8 different cities in the table below. The variable X represents the number of registered automatic weapons in thousands in a given city, and Y represents that city's murder rate. So it's 8 cities, 2 statistics. One is the number of automatic weapons in the city registered, and the other variable is the murder rate. So when you look at, and again, the number of weapons is in thousands, the murder rate is in murders per 100,000 people. Okay, so the first data point is 1213 here. What that means is that this is a city that had 12,000 registered automatic weapons, and clearly I've rounded all these numbers to whole numbers because it's just easier to do the analysis that we're going to do. Normally I would not, and normally we'd have a computer do all the number crunching for us. But there's a lot I want to teach you about relationships between variables. And it's just, a lot of this we're going to do by hand. So it's nice to have nice numbers. Regardless, they don't need to be nice numbers. And everything we'll learn will still apply. Okay, so again, a city that has 12,000 registered automatic weapons, that's X. Y is 13, which means in that same city, at the time that the measurements were taken, there were 13 murders per 100,000 people. So that's the murder rate. Okay. All the murders are murders per 100,000. We're going to go ahead. The first thing we do, and one of the most important things we do to determine if there's a relationship between two variables, is just to do a scatter plot. Now, scatter plots are basically where you look at both number lines and you plot the points as if you're in sort of an XY plane, which is it reveals a lot. It only works when both variables are quantitative. Later on, we'll learn a similar, we'll have a similar discussion when the variables are categorical. And then we'll also talk about cases where one variable is quantitative and the other variables are categorical, but all 3 of these ideas are in 3 completely different chapters of the book. Okay, but as it stands right now, we're looking for relationships between variables. So anyway, the first city, again, 12,000 registered automatic weapons and a murder rate of 13 murders per 100,000 people. So that's just a dot up there. that I have graphed, and let me refresh my page so that you can see it. There we go. Okay, next one is 811 out here, I think. 8,000 registered automatic weapons and 11 murders per 100,000 people. Then 410, okay, that's 4,000 automatic weapons and 10 murders per 100,000 people. Now you have a city with very few automatic weapons, 1,000, and 4 murders per 100,000 people. Then the next one is 712. Okay, and the next one is 37. Then 24, and finally 35. Okay. When it says to describe the geometry of the relationship between the variables, I would say that as x is increasing, y goes up as well. Okay, can you see that? It doesn't, not in every case, okay? But let's say as x increases, which means more automatic weapons, y increases as well. That's more murders. Per 100,000 people. Okay. And then I would just again remind you that the only time you can make cause and effect conclusions in statistics is in the context of a controlled experiment. Nobody's having controlled experiments with how many guns are in a city, and that would be a really hard experiment to do. So when you cannot make conclusions, when you cannot do controlled experiments, then you cannot do conclusions about cause and effect. So this does not imply a cause, oops, I'm just going to say a causal relationship. We still think there may be a relationship between the variables, but not because one causes the other. Okay. Now, so this is going to be called a positive relationship. Okay, because the points go uphill. And so let's just make sure we look at all the different types of relationships here. So that one's positive. I have 3 positive relationships here. So this one's positive, and it's weak. So actually what I wanted to write was a weak positive relationship. Okay, so there's sort of an uphill trend there, but the points are kind of really widely spread. The next one I would say is moderately strong. Positive relationship. Okay, the next one, the points are so close together to, or I should say the points are really close to sort of a line or a curve. When that happens, we have a high degree of predictability. So the strength of a relationship is really about how well you can use one variable to predict another. So this one's a strong relationship. Okay, and I'm going to do a little asterisk here just to define what strong means. So here, strong relationships are those, oops, which allow accurate predictions. Say predictions of y for a given x. Okay. So if you give me, with the strong one, if you give me an x here, I can go up to the curve here and predict a y value real close to these other ones, and it'll be pretty precise. With the weak relationship, if you give me an x, okay, I'd go up and it's like, what should I predict for y? There's a whole bunch of them. And they're so spread out that it just makes, you know, I can make a prediction in the middle of all that, but the margin of error would be bigger there because points are just more spread out. Remember, variability is sort of the enemy of precision. The more variable a variable is, the harder it is to predict the value of that variable. Okay, any questions about that? Okay, so those are strong relationships. These are negative. Sorry, those are positive relationships. These are negative relationships. So this one's a weak negative. Okay, the next one's moderately strong but negative. Okay, and then the next one's pretty darn strong. So this one's a strong negative relationship. Any questions? Does that make sense? I did a data collection with my son on a science project ages ago. What we were making batteries with different electrolytes, and electrolytes are often typically liquids that are inside of batteries that allow electrons to sort of move through, and it creates electricity. And so the electrolyte has to have a pH that's either an acid or a base, which they call alkaline. And so you've heard of alkaline batteries, but also car batteries are acidic batteries. They're not base, they're acid. So the pH measures how strong or an acid is or how strong a base is. And a pH of 7 is neutral. It's neither an acid nor a base. And the idea is that when the acids are strong, you get really good batteries. Oh, but that's actually alkaline. So alkaline has a high pH, so that's a strong battery. Acids have a really low pH, that's a strong battery. But in the middle, where the pH is close to 7, that's a neutral pH, neither acid nor base, and that's a crummy way to make a battery. Very little electricity flows out of a battery like that. This is a relationship that is neither positive nor negative, but there's still a pretty strong non-linear relationship here. Okay, does that make sense, everybody? So we're not going to study the nonlinear ones. The math is just a little harder with nonlinear relationships. And it just takes a lot more time to cover. Okay, it's not beyond you. It takes time to cover. Okay, any questions? All right, so that's for the nonlinear relationships. And then it says sometimes variables have no relationships, as demonstrated below. I had an honor student, I don't know why I agreed to it, but I had an honor student gather data on how many hours someone sleeps a week and their shoe size. And turns out there's no relationship between how many hours you sleep a week and how big your feet are. Okay. So I was allowed to use that data to make a graphic that sort of implies there's no direction in this relationship at all. I don't think you can use sleep hours to predict shoe size. Okay, any questions? Okay, so that's no relationship between two variables. And continuing on now. This is where we're going to start getting into math. We're going to work on linear relationships here. So anytime you look at a relationship that, you kind of feel like, all right, there's a pattern there, and if I was to give it a name, I'd call it something that is sort of where the points are around a line. They won't be on a line, okay? But if the points are around a line, whether it's close or not so close, those are called linear relationships. So see how I'm drawing lines on all of these? Okay, these are linear. Even this first one sort of wants to be around a line, so I'm going to call that linear as well. And obviously I made these all to be following a line, either weakly or strongly. Okay, any questions? But these are all linear. But of course, the nonlinear one with the battery acids. Okay, so we're going to try and find the equation of a line of best fit. That's basically, and this all goes under, none of this is inferential statistics, so there's no probability yet. In module 3, and we're covering 3.1 and 3.2 right now. So in module 3, we're just trying to describe these things. So we'll try and find an equation of this line, and we'll call it a line of best fit. And we have to figure out what that even means. So I think we can go ahead and read here. We want to learn about linear relationships. The first thing we'd like to accomplish is to find an equation of a line of best fit, also known as a regression line. The equation of the line will be y equals a plus bx. So b is the slope. Okay. A is the y-intercept. And I know that you used mx plus b in algebra, but none of the statistics books use mx plus b. And it's because we need Greek letters to go with these and for when we do hypothesis tests. And the Greek letter for m is mu, and that's already used, as you know, in statistics. So they just don't use m for the slope. And that's why the labeling is different here. Oh, and also the Greek letter for A is alpha, and that's already used, but we're not going to do inferences on A, but sometimes we do inferences on the slope. Okay. Anyway, so the slope of the line is B, the y-intercept is A, and we use y hat for points on the line because y is used for actual data points. So you're going to have a y hat, which is the y value on the line, but it's not going to be y because y, those are actual data points here. Got it? So y hat is sort of a predicted value of y. Next paragraph, before we can define the line of best fit, we need to label a few quantities that measure fit. The vertical distance from a point to the line is the difference between their y coordinates. This is called the residual or error. Okay, so a lot of times you want to say error, but in statistics they usually refer to it as residual, but I'll be going back and forth between those two terms a little bit. Okay, so it says residual is y minus y hat. And remember, y is an observed y value. Okay, y hat is a predicted y value. Using the line of best fit, y hat is a plus bx. So someone will give you an x coordinate and you'll predict a y coordinate. That's the idea. Okay. Says the line of best fit should minimize the residuals. These are distances from the line of best fit to a data point. So it says to label a residual for 1 point on the graph below. All right, so I wonder how much I have to label on this. All right, there's a bunch of labeling we have to do. So for this point right here, I'm going to draw a line straight down to this blue line, and I'll explain that in a second. Okay, this point on the black line, okay, and again, the black line is the line of best fit. So this is y equals a plus bx, but we put a hat on the y because those are predicted y values. And actually, I'm a little reluctant to use a point for this point on that line. I'm going to use an x for that because it's not a data point. I want to treat it differently from the points that are drawn with circles. Okay, so that point where the x is, the x coordinate is x, but the y coordinate is y hat because it's on the equation of the line. And you use the x coordinate to compute y hat. Okay, now up here, this data point, the x coordinate is the same, it's x, but the y coordinate is y. That's an observed value in the data set. And you can look it up. I mean, you can see y is 12 there. And that was the city that had 7,000 automatic weapons and a murder rate of 12 murders per 100,000 people. Okay, so that's a real observed data point. But this XY, this thing down, oops, this XY hat thing on the line is just prediction. Okay, and the idea is that, well, you're predicting a certain, and it's about 10 murders per 100,000 people. So if you go from that predicted point to the Y value, it's 10. So this city that had 7,000 automatic weapons registered, we only predicted the murder rate to be 10, but it turns out it was 12, okay? So the difference between those is the residual. It's an error. Okay. So that's this distance here. Okay, so that's gonna be, let's label residual. And maybe in parentheses, that's the residual is y minus y hat. It's a vertical distance, so you subtract the y coordinates. Okay. Any questions? There's a couple of other distances that get labeled here. I think I should go a step at a time. And while I'm thinking about it, let's go ahead and say, the idea here is with this murder rate, sorry, with this city that has 7,000 automatic weapons, I predict the murder rate here to be 10. And that's based on the number of weapons, okay? Anything I go beyond that is sort of an unpredictable part, and that's the residual. The unpredictable part is also called unexplained. Okay, so let's go see what else is down here. It says the deviation from the line of best fit to the mean line is above, they want us to sketch that. So the mean of y coordinates is this right here. So that's y bar. Okay, that's the mean of y values. And that's what the blue line represents. Okay. And they say that that difference, see if I can squeeze this in. Okay, this distance right here is y minus y bar. Sorry, y hat minus y bar. I think my stylus is giving out on me here. Trying to get it to work. Okay. That part has a name as well. And I'll go ahead and give these names. Okay, so the y hat minus y bar is called the explained deviation from the mean. Okay, the residual. So basically, the idea is you tell me how many weapons are in a city, and I will use that to explain the murder rate. Okay, and again, this is not a cause and effect thing, and we do a lot to avoid saying cause and effect. We say, well, one thing helps explain the other, but we're trying to say that that doesn't mean it's a causal relationship, even though I'm saying it explains it. Okay, it's a little hokey. The residual part is the part that you could not have predicted. That's the unexplained deviation. So this this city has a murder rate that's 12, and we only predicted a 10. I can't explain that. Why it was so high. I can explain the 10 because there's a lot of weapons in this city. 7,000. Oh, I said because. That sounds like cause and effect again. So I can explain the murder rate of 10 murders per 100,000, but this goes higher than my prediction. I don't have any way of explaining that right now. Okay, any questions about that part? Okay, and then real quick, there's another deviation, which is called a total deviation here. Total deviation is the deviation from the point xy to the mean line. So we have to just subtract the height of those two y values. So remember, y is y bar on this blue line. So the total deviation, I'll do in a different color here. So let's do it this way. Like that. That's total deviation above the mean. So you can say from the mean maybe. And remember, the blue line is the mean of y values. So total deviation is the y coordinate of the point, which is y, minus the y coordinate of the mean, which is y bar. Okay, and there's not another term for that. We have unexplained deviation, we have explained deviation. If you add those up, you get the total deviation. Okay, any questions? Okay, it says again, a residual is the distance from each point to the line, and we want to minimize all of the residuals. How should we minimize them all together? Next page. Don't see any questions. You guys pipe up and say something if you want to interrupt me. It's all good. Turns out we can't minimize the sum of the residuals. Again, the goal here is just to remember, we're trying to find an equation of a line of best fit, and you can use any line you want. Okay, but what does it mean to be best fit? Well, you have this thing called the residual, which is how far points are from the line. And when the residuals are big, that just means your line is not doing a good job at making predictions. Remember, the residuals are the errors in your predictions. Okay, we don't want the residuals to be big. And we're not talking about just one point, we're talking about all the points. How do we minimize all the residuals together is the idea. Well, we could add them up, but on this page, it turns out we can't minimize the sum of the residuals because they always add up to 0. It doesn't matter what you do, the residuals always add up to 0. So thus, just as variation from the mean is summarized with squared deviations, that's when you compute a standard deviation. You square the deviations and then average those. In the standard deviation, we will summarize total deviation from the line of best fit with the sum of the squared residuals or errors. The sum of squared residuals or errors is denoted SSE. That's sum of squared error. Okay. It measures the variation in Y that's unexplained by the line of best fit. And so that goes back to this notion of the residual being the unexplained deviation from the mean. Okay, we're totaling that up. You can't just add the residuals because they always add up to 0. So we square them and then add. So when you look here, again, this is sum of squared errors. Okay, the errors add up to 0, so we square them. And we're trying to minimize this sum. Okay? Maybe I'll put down here, this is residual. Okay, we want to sum the square of the residuals and make that sum as small as possible. Remember, we can adjust the line. And any line that you draw will give its own residual, a collection of residuals. And we need to figure out a way to get the smallest sum of the squared residuals. Okay, so again, and that's just SSE. SSE is sort of the bad guy. That's basically your total error. Okay. So we're going to use a little bit of algebra to minimize the sum of squared errors. This will yield the slope and the y-intercept of the line of best fit, which is also called the regression line, you may remember. The algebra is simplified if we first take z-scores of every x and y value. The z-score of an x value will be denoted z with an x subscript, and the z-score of a y value will be z with a y subscript. For the FBI data, give the statistics below. All right, so here we're doing 2 variable statistics for the very first time. So I'm getting my calculator out, and I'm going to go ahead and pop over there. How am I going to get the data and the calculator on my screen at the same time? Hang on just a sec. Okay, I got it. All right, so I'm going to pop over and get my camera open. Now I'm hoping you guys can see this. Let me focus it real quick. Yeah, that's good. All right, and then go into data, and then just key all the X's in the first column. Oops, got to clear the memory. And key all the X's in the first column and the Y's in the second column. So we'll go ahead and begin. Okay, and then I'll do the Y's. Okay, so now I'm going to just double check that I've got these all right. Okay, mine look good. Okay, so once you've got all the data in two columns, X and Y, you just press clear, and then you might guess second data, and then you might guess two variable statistics for the first time, which is the third item here. And then it's list 1 and list 2, that's all good. Just hit enter through all of this. And now you have the mean of the X's, standard deviation of the X's, mean of the Y's a little further down, standard deviation of the Y's, and population standard deviation, we know that. So I think we've got all the numbers here. Are there any questions? I'm going to go back to Notability, my app, my Note app, and so we can put some of these values in. So X bar was 5, that's nice. Standard deviation of X was 3.70. I'm going to be precise, 3.7033. Going down the list, Y bar is 8.25. And the standard deviation of the Y is right below it, 3.6936. Okay, so those are pretty precise values. Okay, now the X's and the Y's are printed down below here. Okay, but I did leave a couple, right? So the first X that I left was X equals 4. And to do a z-score, remember, you just do X minus mu over sigma. So here would be X minus X bar over S, because we don't know mu or sigma, use the sample mean and the sample standard deviation. Okay, so our X is 4, the mean is 5, and the standard deviation 3.7033. Like that. So do that. And then shout it out if you don't mind to tell me the z-score of X. That's not what I got.
Professor?
Yeah.
I got 0.2700.
That's what I got too. So negative.
I'm sorry, negative, yeah.
Yeah, negative 0.2700 is what I got also. So that's a z-score of X, 0.2700. And then the z-score of Y, we'll have to look at this 10 now. So y is 10. The z-score, all right, let's put a little zx for the z-score of x. I don't know if you noticed, I just put a little x subscript on the z. And y needs a different subscript because it's a different variable, so zy on this one. And we'll do y minus the mean of the y's over the standard deviation of the y's. And so I think we have all these numbers up above. So y bar, well, so y was 10 minus y bar, I think that's 8.25. Got a mess on my hands. Over standard deviation, which was very precise, 3.6936. Okay, anybody? I want 4 places on this one, if you don't mind. Good. 0.4738 is right. Okay. So that I just wanted to make sure we did one of those. Okay, give me 1 second. Okay, so the next thing is we want to sort of replicate the scatter plot, but instead of the XY plane, I'm going to call this the ZX-ZY plane, and I routinely screw this up, so if you see me make a mistake, let me know. Okay, so anyway, the first ZX is 1.89. And the ZY is 1.28. So I'm actually going to draw some guidelines as I do this. Something's wrong. Hang on. Dang it. Pardon me while I try and figure out my glitch. Nothing wrong with that. Okay, back in business. Don't know why that happened. All right, so the first one again, 1.89 and 1.28 is going to be about here. So just I'm going to draw guidelines as I do this and then erase the guidelines. Next one's 0.81 and 0.75-ish. Okay, my pen has died again. I think my stylus may be dying. That's a tragedy. No, it's working again. Okay, 0.89, 0.81 I should say, and 0.74, about there. Okay, next one is negative 0.27 on x and 0.47, almost 0.5. I think it's this. Next one's negative 1.08. So that's really close to negative 1. And negative 1.15, also close to negative 1, maybe there. Oops. Okay, next one's 0.54. And 1.01. Then negative 0.54. And negative a third, about here maybe. And then a negative 0.81. And negative 1.15. I'll do like that maybe. And then I think last one's, last one is negative 0.54 and negative 0.87. So I'll put that here. Okay. So there's my scatter plot. This, I don't know if this looks familiar to you. Looks very familiar to me because I've graphed this dozens of times over the years. And one of the things I wanted to point out is that while we've done different data points here, these are z-scores of x and y. Just to remind you, well, the original scatter plot we drew was here. I'll just copy that and just make sure you see it. So these data points are they have the same, well, there's some mistakes here, but they have the same data distribution. It's any differences you see are just because I'm no good at drawing, I guess. Okay, so these are the original data points, and they lay right on top of the z-scores nicely. Okay. So all we've done is sort of we've changed the axes. The x-axis is different. The y-axis is different. You may remember z-scores have a mean of 0, so this centers the x's on 0 and the y's on 0. And just kind of puts it into a new coordinate system, but the geometry is the same. Okay. Now, something I just said is that the mean of z-scores is always 0. So right now we're going to go through a list of facts that I need to find the line of best fit. Okay, so here's your fact number 1. The mean of z-scores is always 0. Okay, so I don't know, they're asking me to prove this. So let's see here, z-score, let's see, so it's the sum of z-scores. Z is x minus x bar over s. And they're asking me to divide that by n. Okay, so what I would do is bring the 1 over s, which is a constant, out. And this is the sum of x minus x bar. Okay, and then dividing by n. And so here you have 1 over s. I'll write this as the sum. We can add in different orders. So you can add the x's first and then add the x bars last. Like that. Divide by n. So this is 1 over s The sum of x is fine. X bar is just a single value, and if you add it to itself n times in the sum, then you would get n x bars. Okay, you're just adding it to itself repeatedly, and again dividing by n, and then just take a moment. 1 over s, the sum of x. And then x bar is the sum of x over n. So you have minus n times the sum of x over n. And now maybe you can see it. Dividing by n, that those n's cancel like that. And in the numerator, you have the sum of x minus the sum of x. And of course, that's 0. So the statement is that if you average z-scores, you always get 0. And this is simple. When you take a z-score, you subtract the mean off. You have a bunch of data values. You subtract the mean and you divide by the standard deviation to get a z-score. When you subtract the mean off of a bunch of numbers, you're moving the mean to 0, basically what happens. Okay. We'll need that. Any questions? So this is hard because normally we would do y equals mx plus b. M is the slope. B is the y-intercept. That's normally how you do the equation of a line. And we're saying, nope, we're not going to do it that way. We're going to do it, first of all, instead of y, we're going to do the z-score of y. And instead of x, we're going to do the z-score of x. Isn't that beautiful? Okay, so let me just erase all that mess. This is going to be what I have circled here is going to be the equation of our line, but it's going to be in the z-score plane, z of y and z of x. Okay, so let's read it. It says the line of best fit in this plane is zy hat equals r times zx plus k. The slope is r. You had to come up with a letter for the slope. And the z-intercept is k. It is not hard to show that the z-intercept will be 0. Okay. Remember, z-scores are centered on 0. Okay. So when you go through, all we're saying is that when you draw this line, it has to go through the origin. Because the mean, well, I don't want to use that. I'm going to go ahead and draw a little x here and just say that that's the mean point. Okay, the mean of z-scores is always 0, so the mean of zx will be 0, and the mean of zy will be 0. And all we're saying really is that this line of best fit has to go through the center of the data, which is the mean point. But the mean point has to be 0, 0. So this line has to have a y-intercept of 0. Okay, so that's why we'll go ahead and continue with this. Instead of saying zy is r times zx plus k, we're going to just say zy hat is just r times zx, where r is the slope, and again, the y-intercept is 0. Okay. It says to label a point zx, zy, it's a residual, zy minus zy hat. The deviation from the line of best fit to the mean line and the total deviation. I don't know that I need to do that. Let's go on. It says first we want to find the relationship between the difference of two y coordinates, y2 minus y1, and their z-scores, the z-score of y1 minus the z-score of y2. Okay, so the z-score of y1, if you just take the formula, you would do y1 minus y bar over sy, that's the standard deviation of y. So that's the z-score of y1. And then if we subtract the z-score of y2, this would be y2 minus y bar over the standard deviation of y2. So that's the standard deviation of y. So that's the difference of the two z-scores. And we're going to combine these. They have a common denominator. So you're going to have a y1 minus y bar. Now you're subtracting a difference, which is going to change the sign inside. So you're going to have minus y2. And this is going to be a plus a y bar because of the double negative. And then this is over the standard deviation of y. Like that. And the y bars cancel. So you just get y1 minus y2 over the standard deviation of y. Okay. Now I want you to see, first of all, this thing is telling us, I'm going to make some space real quick. And by the way, this is just, all of this is just setting up some algebra for a pretty complicated argument I'm going to make in a sec. Complicated compared to some of the other things we've done in this class. But you won't be doing anything like this on an exam. My job right now is to explain where these formulas come from. Okay, so that's the difference of the z-scores. I want to make sure you see what this is telling us here. This is saying if you take the difference of two z-scores, zy1 minus zy2, that this is the difference of the corresponding y values, y1 minus y2 over the standard deviation of y, like that. And then if you multiply the standard deviation of y on both sides, okay, I'm going to put an sy there. And do the same thing on the other side with an sy. I'm trying to. Dog just came in. Little sy here, and then surround that in parentheses. The sy's cancel on the right side, like that. And what this tells you is that the difference between the y coordinates can be expressed as y1 minus y2 is the standard deviation of y times the difference of the z-scores. Okay. And we'll use this a lot. Okay. In the next step, they square it. So if you look at y2 minus y1 squared, now it's changing the order of these. So I'm going to write this as the changing the order on the other thing. So you can take standard deviation of y. This will be squared because it's squaring it. And then subtracting the z-scores, z-score of y2 minus the z-score of y1, and square that. Okay, so that's for any two y values. If you take the difference between them, oops, this should be z-score of y1 here. If you take the difference between any two y values and square it, that's the same as the distance between their z-scores squared times the standard deviation squared. Okay, so there's that. And we'll use that several times in the argument. This is just an algebraic statement that will help me a little bit later on. Okay, now we're getting close to that next page where the big boom falls. Let's go ahead and talk about standard deviation real quick. Here's the formula for standard deviation that we have not looked at in some time. Let me read this. It says, next, the sample standard deviation formula is this. Squaring this gives a formula for the sample variance, right? It says, rearrange this to find a formula for the standard, for the sum of z squares. Interesting. So remember, z is x minus x bar over n. So they want us to make this into a sum of z squared. I think I see how this might work. So first of all, if I write s squared as the sum yeah, there's a typo in the formula. First time I've noticed this in forever. And I don't think it makes a difference. But so we have the sum of x minus x bar square. That is over n minus 1. Maybe you see that I did not put the n minus 1 inside the sum, and that's in fact because it's usually not supposed to be in the sum. Doesn't matter. I think it gives the same thing. So multiply by n minus 1, both sides, like that. And then divide by s squared on both sides. Okay. And what you end up with on the left is the s squares cancel. On the right, the n minus 1s cancel. Like that. And what this becomes is just n minus 1 on the left equals the sum. I'm going to put the s squared inside the sum. That's just the distributive property. So I'll write the sum of x minus x bar squared over s squared. Or maybe write this as the sum, watch this, of x minus x bar over s. Everything is squared here, so I just group it together and square. And that x minus x bar, oops, I made a mistake for the z-score formula up above. Just as a reminder, the z-score is x minus x bar over not n, but the standard deviation here. And that's what you've got there. So this is the sum of a bunch of z-scores squared. So that's a crazy consequence, that any collection of z-scores, it doesn't matter what the data set is. If you take all the z-scores of those values and you square them and you add them up, you get n minus 1. So if there are 10 z-scores and you square them and add them up, they will always add up to 9. That's what this says, which is absolutely bizarre. But it's always true. And it doesn't matter what the numbers are. You just pick 50 random numbers, take their z-scores and square them and add them up. It'll add up to 49. Okay, so, and here's the proof. Okay, so then it says last, how do we determine the vertex on the graph of a parabola? Okay, so this is, I said, under what conditions is this the lowest point? So this is, this sort of assumes that at some point in your life you took an algebra class that covered parabolas. And I think it's safe to say that that would be true for most of you. So this is a parabola. Okay, and I'll just go ahead and put a coordinate system on this. The lowest point, if the graph opens upward, then this is the lowest point. It's called the vertex Again, under what conditions this is the lowest? So it's the lowest. I'll do an asterisk here and say it's lowest if the parabola opens upward. Okay, and that happens if A is positive. So maybe I'll even put that in there. When A is greater than 0 on the equation of a parabola. And then we know the parabola opens upward. So this is all info from an algebra class. I think normally you would cover the graphs in an Algebra 2 class. At MathSac, that would be Math 71. So maybe some of you have taken Math 71 and you remember this. Okay, what we're interested in is not actually the value of the y-coordinate, but I want to know what x is at the lowest point. Okay, and by the way, the lowest point is called a vertex, which is a weird word in math because it means lots of different things depending on what the context is. Sometimes the vertex is the lowest point, sometimes it's the highest point, sometimes it's on the left, sometimes it's on the right, sometimes it's the corner of a square or a polygon. Those are called vertices also. Anyway, on a parabola, the vertex always occurs where x is negative b over 2a. And maybe some of you remember that and maybe you don't. Okay, so the vertex always occurs where x is negative b over 2a. And I could explain that, but that's a 20-minute talk also. So just trust me. All right, now it's 10 o'clock. Let's go ahead and take our break now. So let's do a break till 10:10. Okay, so just to summarize here, we've got a couple of important ideas that I wanted to just kind of nail down real quick. First of all, z bar is 0. It doesn't matter whether you're doing x's or y's, the mean of z-scores will always be 0. Got that? Second thing, that if you take two y values, it doesn't matter what the y values are, the difference between them squared is the same as the difference between their z-scores squared times the variance, which is the standard deviation squared. Okay. And then finally, down below, just one second. Somebody has drawn on the whiteboard. Is there any way to get rid of that? I don't know if that's possible. So is somebody sharing a whiteboard? Because there's a mark on the screen that somebody drew. I wonder if I can clear that. Okay, I'll start the share over again. I'm sure it was an accident. Or maybe it was me, I don't know. Okay, that's better. Okay, so I'm gonna try that again, you guys. Okay, so as I said, there's a handful of things here. First, the mean of z-scores is always 0. If you take a difference between two y-coordinates and square it, that's the same as the difference between the corresponding z-scores squared times the variance of the y-coordinates, or that is the square of the standard deviation. Also, a crazy thing is if you take any data set and compute all the z-scores and square them, add them up, you always get the number of values minus 1. Finally, the vertex on a parabola will be used. Remember, we're trying to find the smallest sum of squared errors. Squared is another word for quadratic. Quadratics have graphs that are parabolas, and we know how to minimize a point on a parabola. If it's y equals ax squared plus bx plus c, this is minimized when x is negative b over 2a. Okay, we're going to try and minimize the sum of squared errors, which comes in here. So it says we want to minimize the sum of squared residuals from the regression line, which is SSE. The expression is quadratic, so we should be able to use the formula for the vertex of a parabola to minimize the sum of squared errors. Remember, the vertex of the parabola is this value here. Okay, so here we go, sum of squared errors. Whenever we square things, that's quadratic is the word for it. Okay, so first thing we see the difference between y and y hat. So that's the difference between two y coordinates, and we have a rule right here that says, well, you can just take the z-scores of those differences and subtract and square and then multiply by the square of the standard deviation. Okay, so I'm going to write this as the sum of sy squared, then the z-score of y minus the z-score of y hat, like that, squared. Now, the z-score of y hat is actually the equation of the regression line. So remember, this is the equation of the regression line, and the zy, zx plane, maybe I should show that here. This is the equation of, this is the regression line, or the line of best fit. And we said that the equation is z y hat is the slope, which we called r, times z score of x. So zy hat is r times zx. Let's put that down below. Okay, so we can rewrite this as this, and the standard deviation I think we could just factor out. So let's write sy squared in front of the sum. And here we have the z-score of y minus the z-score of y hat, which is r times the z-score of x. And we square that. And now I'm actually going to square this monstrosity. So I'm going to do a little cleanup work. So I think I need the space. All right, so this is equal to standard deviation of y squared times the sum. And here we go. First of all, you square the zy. So this is going to be zy quantity squared minus, and I'm doing the whole FOIL thing. If you do like, you know, x plus y, let's do x minus y squared from algebra. It's x squared minus 2xy plus y squared. So that's an algebra thing. So here I have to do minus 2 times zy, or there's an r actually, and then we'll say zx zy, like that. And then plus the square of the second thing, this would be an r squared zx squared, like that. Okay. Okay, and then the sum of a bunch of things added together, you can add in any order you like. So I think I would write this as sy squared, maybe some parentheses, and here go a few things added together. First, the sum of zy squared, okay, minus the sum, and I'm going to change this, but so you can have minus the sum of this 2r zx zy And so you're adding a bunch of things together. Now the R is a constant in every term in the sum, but the z-scores change from term to term because every x and y is different. There's only one R, and the 2 is separate too. So these are in a sum. You can factor out common factors in a sum. So I think I would rather write this part with the 2R factored out, and then just the sum of the z-score of x times the z-score of y. And then plus, we're still summing here, we have the sum of r squared zx squared like that. But again, r is a constant that does not change. It's just the slope of a line, and you can factor that out. So as before, I think I'd rather have that out front. So this would be r squared times the sum of the z-score of each x value squared. Okay, then a couple of things to remember. First is that the sum of the squares of z-scores is always n minus 1. This statement right here, that if you add up a bunch of z-scores squared, you always get the number of values minus 1. So let's do that. The sum of this z-scores of y squared should be n minus 1. And the sum of the z-scores of x squared should be n minus 1. Okay, so you can rewrite this as sy squared times, first of all, just an n minus 1. And then minus 2r, sum of zx, zy, plus r squared times the sum of the zx's squared. That'll also be n minus 1. Okay, now this is a quadratic in R. Maybe I would write it this way. It's an n minus 1 r squared minus, how about this, 2 sum of zx, zy, and that's times r, plus just an n minus 1. Okay, so again, that's a quadratic in R. Okay, and I'm going to make a little space. Where do I do this? Okay, so remember quadratics look like ax squared plus bx plus c here. The a is the x squared coefficient, the b is the x coefficient, and the c doesn't have a variable, that's a constant. Okay, so here it's in R, but then the n minus 1 is the a. This negative 2 sum of zx, zy, that's the b. And then the constant is c. Okay, so the quadratic, I'll make a note on the left here that the quadratic in R is minimized at the low point of the parabola. That's the graph of the quadratic. So to minimize the point on a parabola, you have to go to the vertex where x is negative b over 2a. So I don't mean x here, I mean r. So this is minimized if r is negative b over 2a. Okay. So using the a, b, and c here. So the negative of b, notice it's got a minus sign in front already for the b, right here. So the negative of that will drop the minus sign. So you'll just get 2 sum of zx, zy over 2a. A is n minus 1. So So you'll do 2 times n minus 1. Okay, and we can cancel these 2's. So this is the formula for the slope in the zx, zy plane. R has to be the sum of zx times zy over n minus 1. Okay, and that's a super important number in statistics. Okay, and we'll have all kinds of things that you need to know about R. It started off as being the slope of a line, but it's going to be a lot more than that. I'm just going to pause for a second and give you guys a chance to catch up, but also chat any messages if you have any. Now, I want to rearrange that statement to come up with an expression for the sum of zx times zy. So from this statement here, note that the sum of zx, zy is multiply both sides by n minus 1, so you get n minus 1 times r. Okay. And I want to use that up above in this algebra that we're doing. So you still have the sy squared, and then there's an n minus 1 r squared minus 2, and then the sum of zx, zy can be replaced by n minus 1 times r. So I'm going to use this effect here. So it would be 2 n minus 1 r, but then there's another r, okay, and then there's plus another term, the n minus 1 term, so just plus n minus 1. And it doesn't take a genius to see that there's a bunch of n minus 1's here. So I probably want to factor n minus 1 out. Okay, so if I factor the n minus 1 out, I'll have an sy squared times n minus 1 out front. And inside you have an r squared minus 2r squared plus 1. Turns out this is sy squared times n minus 1. So r squared minus 2r squared is negative r squared, so we would just write this as 1 minus r squared. Interesting. Okay, so that's the sum, that's the minimum value of the sum of squared errors from the line. Okay. So any questions about this? And if that blew your mind, don't worry too much, because we're gonna not ever repeat that. We do need the consequence, which is the formula for R and what R is doing. Okay, but I don't think you're gonna ever do an argument like this again. So anyway, the equation of the line of best fit in the ZY-ZX plane, we said it was the z-score of y hat is r times the z-score of x. Oops. The z-score of x. Okay, and then if you want, we could put this into the xy plane. So if we just rewrite things, let's remind ourselves that the z-score of y hat would just be y hat minus y over the standard deviation of y. And the z-score of x would be just x minus x. Oops, y hat minus y bar. My bad on this one. Do you guys see that mistake right there? It's just subtracting. Z-score of x is x minus x bar over sx. Like that. And then, so if you take this zy equals rzx, you're going to get an equation of the line in the xy plane. Okay, so zy hat is y hat minus y bar over sy, okay, equals r times x minus x bar. This should be the z-score of x down here. I'm sorry, I gotta stop making mistakes. Okay, x minus x bar over sx. And then I am going to multiply both sides by sy. To cancel that. Okay. So you end up with a y hat minus y bar. I'm trying to solve for y. So y hat minus y bar is equal to, I'm going to put these constants together and write, we've multiplied by sy, so I'm going to put that with the r, so it's going to be r times sy over sx. That's going to be the slope of the line of best fit. And then times x minus x bar. Okay, so those are the same. That is the equation of a line in what we call point slope form. From algebra. Okay. And it's worth noting that the point is x bar, y bar. Okay, this is telling you that the point x bar, y bar, which I call the mean point, or sometimes it's called the centroid, is sort of the center of the data set, x bar, y bar, that point is always on the line of best fit. And the slope is this thing in front of the x factor. So the slope will be r sy over sx. Okay. Now, so we'll make a note of this. Note x bar, y bar must be on the line of best fit. That'll help us graph it. Okay. Now if we solve this, I want to solve this for y hat. So I'm going to have to distribute here and write y hat, y hat minus y bar equals r sy over sx times x minus r sy over sx times x bar. And then I'm again trying to solve for y hat. Y hat is equal to r sy over sx times x plus, in parentheses I'm going to write y bar minus r sy over sx times x bar. Okay. So this is slope-intercept form. for the equation of the line. So this is the slope, and this other thing is the y-intercept. Okay. For the line of best fit. The slope of the line is r sy over sx. The y-intercept is y bar minus this r sy over sx. That's just the slope again. So I'm going to just write the word slope times x bar. So this is going to give this line that we were looking for. John and Susan, x, b, x hat in the equation. Okay. Okay, so again, all very theoretical. What point is always on the line of best fit? The mean point. And we put this, I've got this up here. So the mean point, AKA the centroid, x bar, y bar. Again, you'll be graphing this line, so to find the mean of the x's and the mean of the y's is to find one point on the graph of the line of best fit. Okay, any questions about that? And by the way, the other point will be the y-intercept. So if you graph the mean point and the y-intercept, you can draw a line of best fit. Okay, it's a little bit of computation to get to the y-intercept. The good news is that the calculator does this automatically. Okay, now there's a couple more sum of squared values that we have to compute. So just do a little more reading. We also want to measure the total variation of points from the regression, points on the regression line from points on the mean line. The sum of these squared deviations from the regression line is denoted SSR. It measures variation in y that's explained by the line of best fit. So the R here stands for regression, not residual. And regression is the line of best fit. Okay, so this is called the total. No, I don't want to use the word total. That's confusing. So this is the explained deviation or variation. Okay, so you're taking y hat minus y bar. Got it? If you go back to the graph we did way in the beginning. Not that one, this one. Remember, the explained deviation was y hat minus y bar. That's the difference between the mean value of y and the predicted value of y. We're saying, yes, I can use the number of weapons in a city to explain a certain rise in the murder rate for that city. It's not cause and effect. But the explained deviation is when you use x to predict y. That prediction is called y hat. And the deviation above average is y hat minus y bar. Okay, that's the explained deviation from the mean. It makes sense because you're using the number of weapons in the city to predict it. Okay. So explained deviation is that deviation which is predicted by the line of best fit. Okay, so going back down, they want us to get a value for this total explained variation from the line. Okay, so we know that this SSR explained deviation We can always take a difference of y coordinates and say, oh, well, let's take the standard deviation of y squared and subtract the corresponding z-score. So this is the z-score of y hat minus the z-score of y bar. Okay, squared like that. Now you need to remember that the z-score of the mean is the number of standard deviations from the mean. So the z-score of y bar is the number of standard deviations that y bar is from the mean, but y bar is the mean, so this would be 0. Okay, z-score of a mean is always 0. So what you have here is the sum. Oh, and by the way, the z-score of y hat, that's just the equation of the regression line. That's r times the z-score of x. Okay, so remember the equation of the regression line in the z plane was z y hat is r times zx. So that's the regression line in the z plane. So that's what I'm using down here. So in the end, you get s, y, and I'll factor the standard deviation out, or the variance out. Okay, so we're going to write sy squared sum of zy, which is r times zx, and that's going to be squared. So r zx, we'll put in squared like that. But the r is a constant. It's actually an r squared, so I'll factor this out as sy squared times r squared. And then you have the sum of the z-scores of each x value squared. And we know that those always add up to n minus 1. Okay, from one of the rules we made in the beginning. So in the end, I'm going to squish this a little. Let's just get one more statement in here. Okay, so in the end, I guess this is just, I'll write n minus 1 sy squared times r squared. Okay, so that's called the explained deviation from the mean. Or variation, if you like. Okay, and then the total variation goes back to the graph again. So I'm going to slide back to the original graph, and I'll come right back here again. So back to that original graph right here. The total variation of y coordinates is deviation from the mean. So you take each y value and you subtract the mean, and notice that the expected deviation plus the unexpected deviation, those add up to the total deviation. Okay, and the total deviation is y minus y bar. So let's go back down. Now we're doing the total deviation for all the points. So we're taking that y minus y bar here, squaring it and adding it for all the points. Okay, they're asking us once again to simplify this. So we know that the difference of two y coordinates is just the standard deviation of the y coordinates squared times the difference of the corresponding z-scores. So this would be the z-score of y minus the z-score of y bar. But again, the z-score of y bar is the z-score of the mean, and the z-score of any number is the number of standard deviations from the mean. Y bar is the mean, so it is 0 standard deviations from itself. So that's going to be 0 right there. And so in the end, you just get, I guess in factor out the standard deviation because that does not change from term to term. So the variance, I guess, is what that is. And then sum of the z-scores of each y value squared. But as we remember, The sum of any collection of z-scores is always the number of them minus 1. So this is just n minus 1 times s squared. sy squared, I guess I should say. Okay, now it's asking me to do a little bit of adding. So first of all, SSR plus SSE, and then label it by what it measures. Okay, first of all, SSR plus SSE. Let's go back up above. SSR is up here. Okay, we'll put that in. That's n minus 1 sy squared times r squared. Oh, I think I screwed up. Hang on. Up above. Oh, that's right. Sy squared times r squared. And then plus SSE, that's the one that's further up. Where is it? Right here is SSE. Okay. So sy squared n minus 1 times 1 minus r squared. So it's really similar. N minus 1 sy squared, and then this has a 1 minus r squared, like that. Once again, there is some factoring you can do. How about if we go a line below and factor out the n minus 1 and the sy squared? And if you look, what's left inside is an r squared plus a 1 minus r squared, and the r squares cancel. So that's just 1 in the parentheses. So what you get is n minus 1 times just sy squared, but that turns out to be SST. Okay. Now to label what these mean, you've got to remind yourself that SSR is the explained deviation or variation. Plus SSE, that's the unexplained, that's the residual, total, the sum of the squared residuals. So we call that the unexplained variation. And it's fortunate that when you add those up, you get the expression we got for total variation. So those really are two components of variation. Total variation, the sum of the unexplained part and the explained part. Explained, remember, is just that part that is predicted. So we predicted murder rates based on the number of automatic weapons. So we're using the number of automatic weapons to explain part of the murder rate, but another part is unexplained. Okay, now it's asking us to do something. We've shown from this, let's just add this in red. We've shown that SSR, the explained part, plus SSE, the unexplained part, is equal to SST, the total variation. And now it's asking us to divide this. So if you take SSR plus SSE, this equals SST. And they're asking us to divide these by SST. So if you divide by SST, on each side, it tells you that if you take the proportion of total variation And I'm going to make some space to write below this. So SSR is the explained variation out of all variation. Okay, that proportion of variation that's explained by the number of automatic weapons plus SSE over SST, that proportion of total variation that's unexplained, okay, by the number of weapons in the city. What do those add up to?
One.
1, correct. So I'm adding some notes under all this. Unexplained proportion and my explained proportion have to add up to 1, which is the same thing as 100%. So they're asking us to tell us how you evaluate SSR over SST. So we have the thing we've gotten out of this is that SSR over SST, it is the proportion of total variation that's explained by our explanatory variable. I should say total variation in Y that's explained by X. How about that? Remember, we refer to X as the explanatory variable, and this discussion we're having is why we call X the explanatory variable. Okay, but it's not 100% explanation. It's part of an explanation. Okay, well, what part is what we're explaining? How much is X, explaining Y? How good of an explanatory variable is it? Well, SSR is somewhere here. You can see it up above, it's n minus 1 sy squared times r squared over the total variation, which is just n minus 1 times sy squared. Okay, and of course there's cancellation. And remember, r started out as the slope of a line. Okay, how are we doing for time? We're doing great. But r squared is something else. Now your calculator will just compute r for you. So we type the numbers in, and the calculator just tells you r, and we'll look that up in a second. But r squared you have to compute, so you just take the r value from your calculator and you square it. Okay. What is r squared? Well, r squared is a proportion of total variability that's explained by the variability in y that's explained by your explanatory variable. So if you put this into words, you're saying that there's a lot of variability in murder rates, okay, but some of it can be explained by how many guns are in a city, how many automatic weapons are in a city. Well, how much? Well, r squared is the proportion, and we'll compute that in a minute. Okay, now, first of all, r squared is a proportion of SSR over SST. Proportions must be between 0 and 1. So we know that r squared has to be between 0 and 1 because it's a proportion. Okay. You have a part over a whole. The part could never be less than 0, and it could never be more than the whole. So the proportion has to be between 0 and 1, or 0 and 100% if you like. So 1 is the same thing as 100%. 0 is the same thing as 0%. So this is true for any proportion. Okay, now if r squared is between 0 and 1, that means r is going to be between -1 and +1. Remember, some of these lines go downhill, and r was the slope of the line. R is the slope of the line. In the ZX, ZY plane. Okay. So we expect R to go negative if the line goes downhill. Okay, so we know R will always be between -1 and 1. It never gets bigger than 1. It never gets less than -1. Okay, any questions here? Notice if r goes between -1 and 1 and you square it, it'll go positive. So r squared has to be between 0 and 1. Okay, any questions? As I say, r is a super important number. So anything I say about r is something you would be expected to remember. Okay, so there's all this algebra stuff, nobody's going to ask you to remember this. Okay, not even, I mean, maybe the formula, but I'll provide formulas. Okay. I mean, we had a formula for r somewhere here. There was where we just, right here is where we discovered the formula for r. So I'll summarize that somewhere. Okay. Then later I gave formulas for the slope and the y-intercept. Okay. I'll provide those as well. We'll summarize them somewhere. And then the next thing I said that was super important was that r squared, oops, that r squared, hang on, r squared is the proportion of total variation in y that's explained by x. I think that's going to be super important. And now r squared is between 0 and 1, which tells us that r is between -1 and +1. Okay. And r is also the slope of the line. Okay. And then we've got some names. So r squared is called the coefficient of determination. I don't know who came up with that. It sounds super important. Because it determines how good of an explanatory variable it is that x is for y. Okay. It explains how good x is at determining y, or explaining y. How do we interpret r squared? Well, I think I would just copy this statement here down. And how do we interpret r squared? This way. And that's important. Okay, so r squared is called the coefficient of determination. R gets a different name. R is called the correlation coefficient. Actually, its official title is the linear correlation coefficient. Correlation, coefficient fishy. Okay, it's talking, right? Okay, so correlation is just another word for a relationship. It tells us about the relation, the correlation between X and Y. So it tells us about the relationship. Between X and Y. Okay. Tells us about it. Okay, so what is the value of SSE when all points are on a line? Now remember, SSE is the sum of squared residuals. Got it? The residual is the distance from a line, from the line to the point. So what is the residual when a point is on a line, on the line of best fit? That's a question for you. What's the residual for a point that's on the line of best fit? And remember, the residual is the distance from the point to the line. 0. So if all the points are on the line, then all the residuals are 0. And so the sum of squared residuals will be 0. Okay. So now it says, what is the value of r squared when all the points are on a line? Well, remember, SSR over SST plus SSE over SST is always 1. SSR over SST we determined was r squared. Okay, and we've decided when the points are on the line, then SSE is 0. So this thing is going to be 0. So what's the value of r squared when all the points are on a line? R squared will be 1, which tells us if r squared is 1, it tells us r is plus or minus 1. You guys follow me on this? So if the points are on a line, r squared is 1, so r will be either positive 1 or negative 1 when the points are on a line. What is the value of r when the points are on an uphill line? Anybody? Remember, r is the slope of the line. So if the line is uphill, this is the slope in the ZYZX plane. So if the line goes uphill, the slope has to be positive, so r will be 1. What is the value of r when all points are on a downhill line? Negative 1, because r is the slope. So if the line goes downhill and the points are all exactly on the line, then r will be negative 1. Okay. What's the value of r when none of the variation in y is explained by a line of best fit? None of the variation. Ugh. Well, let's see here. We have SSR over SST plus SSE over SST is equal to 1. This part is the explained, this is r squared, which is the explained proportion. Actually, I don't need this whole statement. Let's just write it this way. R squared is the explained proportion. This is all we need. I'm going to delete that. So R squared is the explained proportion. And they're saying none of the variation in Y is explained by the line of best fit, or by X really. So what I want to say by the line of best fit and X, I think I'm going to add to this. X is the explanatory variable. None of it's explained. So that means that the explained proportion would be 0. Any questions? Okay, so if the explained proportion is 0, then R squared is 0, which means that R must be 0. Any questions? Now remember, when points are close to the line, we call the, and this goes way back to the beginning, so I'm going to slide back a bit. We said when R is on a line, sorry, when the points are on a line, then R is 1. If the points are close to a line, then R is approximately 1. Okay, if the line goes uphill, R is approximately 1. If the points are close to a line and the line goes downhill, well, R should be close to -1. Remember, it's exactly -1 when the points are on a line that goes downhill. Okay, so when the points are close to an uphill line, R will be close to 1. When the points are close to a downhill line, then R will be close to -1. Now, with the moderate cases, if the line goes uphill, R will be closer to like a half. Okay, so we'll say 0.5. Now let me be a little more precise. I think we go with a 0.8. Let me look at this table that I've made. So what I had said is that the moderate cases, we're going to say 0.5 to 0.8 for moderate. That's fine. So back to the graphs here. So let's change this notation here a little bit. So I'm going to change all of this actually. So with the strong relationship, we're going to say R is between 0.8 and 1. Okay. For the moderately strong, the table said 0.8. Oops, sorry, 0.5 to 0.8. Okay. And then the weak relationship that's positive will have R between 0 and 0.5. Okay, how about that? And when R hits 0, there's no relationship. So I wanted to jump down. I'll give you a second on this. And then with the no relationship picture, that was the shoe size versus sleep hours per week for a given person. I think R will be close to 0 on that. I don't see any linear pattern there. Now the difficult thing with the case, the nonlinear case, let's do nonlinear a sec. Okay, so no relationship is where R is close to 0. We talked about that. Okay. then with the negative relationships, I'm going to go back to that chart again and just use its notation. So that when it's strong negative, your R should be between -1 and -0.8. Okay, and I'm okay with an or equal there. Doesn't matter. And with a moderate negative relationship, R is going to be between -0.8 and -0.5. Okay. And for the weak relationship, R will be between 0 and -0.5. Okay. And of course, R can fall between two cases. So if R is exactly 0.5, then you can just say either one, I guess, or both. Okay, so again, when R is positive, you get an uphill relationship. When R is negative, you get a downhill relationship, and R tells you how strong the relationship is. And then if R is 0, there's no relationship. But then there's this case where R is both positive and negative. So for part of this, R is going up. I mean, the graph goes uphill. And then another part, it goes downhill. And so R is positive on the uphill side and negative on the downhill side. And in the end, combining those, your R comes out to be 0 here as well. So with the nonlinear, if it's very nonlinear, your R will come out 0, approximately. And that's the same as if there's no relationship at all. So R is not good at finding strong relationships that are very nonlinear. And it's not good at distinguishing that from the case where R is 0 because there's no relationship at all. Okay, now there are measures that can find these strong relationships that are nonlinear, but we're not covering them here. They use a capital R for the nonlinear ones. And the same thing's true. There's a measure for the nonlinear ones that flags when that happens. Okay, so we got all this. This is good. Let's slide back down. So this is the table basically that talks about R values here and how we interpret them and the strength of a relationship between two variables. Okay, and I pretty much covered that already. 0.8 to 1 is strong on either side. 0.5 to 0.8 is moderate on either side. And then between -0.5 and +0.5, those are weak. And then at 0, there's no relationship. How about no linear relationship? But there may be a nonlinear one. Oops. Okay, any questions about all that? Ugh. Okay, so I'm going to take a 2-minute pause for you guys to catch up here. And ask Okay, are there any questions, anybody? All right, so again, the theoretical developments, not going to be tested on, but whenever we talk about R and its meaning, I will be asking questions about that. So this whole issue about strong relationships, weak, positive, negative, or no relationship, or the nonlinear relationship, all of those ideas are going to be important and are fair game on an exam. Okay, not the upcoming exam, so I won't ask you about any of this till the final. Okay. Now, just a quick reminder about what R is. Let's go on down here. It's just telling us to compute R here. So just a reminder, this is the same data, but just as a reminder, R is the sum of Zx times Zy over n minus 1. So we're going to compute that here. We've already computed those two missing z-scores. So I have to go back and grab those way back here. Okay, so copy that to this page here. Oops. Okay, so here are those two values. Go ahead and grab those. And this formula for R tells us we have to multiply Zx times Zy. So we've got all the Zx's and Zy's, but now we need to multiply. And I don't know, I'm going to keep 4 places, even though we're going to have way more than that on our calculator. So the Zx times the Zy. Okay, so for the first pair, I got 2.4308. Okay, the next pair. And if somebody wants to add these as I go, you don't have, you can pause on the multiplications and just start adding these. The next is 0.6031. So you've got 2 numbers to add and then continue. Okay, so 0.7438. I don't think that's right. No, it's okay. 7438. It's negative on this one. So make sure you subtract this one if you're doing the running total. Okay, this one's 1.24228. Negative times negative is positive on that one. Next was 0.5484. Okay, so I'm sure there's a mistake on the one that I did that was negative. I don't know why I got that, so I have to check what I did wrong back there. Anyway, this one I just did is 0.1828. Nobody's putting in a correction. I'm sure this middle one's wrong, and I'm sorry if you're adding these up. Let me try it again. Okay, so that's better. It should be 0.1279, and I don't know what went wrong before. Okay, so I'll highlight that in green. The one I'm highlighting was wrong before and is corrected now. Okay, keep going. So next one's 0.9321. And the last one, 4752, I think. Should be negative. Yeah, nutsy. So for the poor souls who are adding this up, you could subtract out the 0.1297 and then subtract it out again because it was supposed to be negative. So if you have the total, just subtract out the negative 0.1297 twice. Andrea, thank you for the total. Did you do that with a negative on the 0.1297? Oh, thank you so much. So 6.2873. Okay. So again, the R value is the sum of Zx times Zy, which we just did. It's the 6.2873 over n minus 1. N is the number of points. I think there's 8 points here, so it'll be 8 minus 1. So you just divide by 7. So I get, nope. 6.2873 divided by 7. 8982, I think. Okay, and notice if you go back up here, 8982 is like right in the middle here. 0.8982 is our R value. Okay, so that indicates a strong relationship between X and Y. Okay, so here the relation between the number of automatic weapons. Again, these are registered. And murder rate. In cities is strong. So that's telling us that X is a good explainer of Y. That is, the explanatory variable is good at predicting the murder rate. Okay. What else does it ask for? Does it ask for R squared? Yeah, it says R squared here. So let's do R squared real quick. R squared would be this 0.8982 squared. So that's a 0.8067. Now that's a proportion. You convert proportions to percentages when you interpret them. So 80.6% of variation in murder rate the rising and falling of murder rate. You get the idea? In murder rate can be explained by the number of registered automatic weapons in a city. Wow. That's a big deal. But then again, the trap is to sort of turn this politically. And political is a huge trap these days. To turn this politically is to say that there's a causal relationship, and we know that we cannot say that. Is the murder rate caused by people buying and registering automatic weapons? I always say, you know, just to kind of turn that around, people buy weapons to protect themselves lots of times. So sometimes I think the number of weapons is caused by the murder rate. It's just as valid as saying it the other way around. And in the end, we don't know. Okay, we just don't know. So you gotta just say, look, there's a relationship. It's strong. The one is not causing the other. At least we have no evidence of that. Any questions? They want the slope and the y-intercept. So just to back up again here, the slope of the line of best fit, the formula that we came up with way up here, I think. Way up here. In fact, let me just copy this over. Because we'll need both of these. Oh, went too far. Did I? Yeah. Okay, so here are the formulas that we came up with. Okay, so let's, first of all, we know what R is now. So we can say the slope is R, which is 0.8060, sorry, 8067, times the standard deviation of Y, which we did a long time ago, over the standard deviation of X. By the way, this is a rise over run, just like slope is in algebra. The rise is related to the average rise in Y. And the run, you know, standard deviation of Y is the average change in Y, and Y is vertical, so that's the average rise. Standard deviation of X is the average run in X. So it's still a rise over run, and multiplies by R, which kind of mixes the strength of the relationship in, and also makes R makes this negative when the slope should be negative. That's a good thing. Anyway, SY, we got to go all the way back for SY and SX. Way back. There they are. Okay, so I'm just going to copy all these actually, because we're going to need all of them. Here. Okay, so these were X bar, SX, Y bar, and SY from before. So when we compute the slope, or no, so yeah, the slope, you need to multiply by SY, which is 3.6936 over SX, which is 3.7033. Okay, so let's do that real quick.
Why do you put R squared instead of R? equation for the slope?
No, I don't think so. I don't think, no, it's not. that,
Isn't R 8.8982?
ooh, I see what you're telling me. And that makes you right. And me wrong. Again, 8982. Good job. Thanks for being there. Okay, now let's do it. You're the best. Thank you. Okay, so the slope of that line is 0.8958, I guess I'll say. Okay. And then the y-intercept is y bar, so that's 8.25, minus the slope, which was 0.8958, times x bar, which is just 5. Okay, I hope I did this right. I got 3.771. Now, okay, so on your TI calculator, the TI 36X Pro, the slope is, well, let's just look. So I'm gonna pop over to my camera again and try and focus it. Now you may remember we keyed in all the values, and you do not have to do any of the computations that we've done by hand today. Okay, on your final exam and your homework, again, you put the x's in the first column and the y's in the second column, and just remember to do 2 variable stats here. So that's the third thing. And if you hit 2 variable stats, and it's easiest to go up from the bottom. So instead of scrolling down, scroll up, and it goes to the bottom of the list. And if you get R right, then you're golden. So R was it 8982? Is that what we got? $8982, exactly right. SY, SX, the slope was 8958, the y-intercept 3771. Everything's exactly right here. 8982, 0.8958, and 3.771. Okay, identical to what the calculator gives. So you don't need, please don't ever compute these by hand again. On your homework, just key the x's in the first column, the y's in the second column, A, B, and R will be here. Any questions? We got 1 minute left. So the slope is A on the calculator, and the y-intercept is B on the calculator. So that's reversed from how I started the lesson. But calculators all use different notations, and it's very frustrating from what the books use. All right, but you can get the slope, the y-intercept, everything from the calculator, and then it's asking us to graph this, and this will be the last thing we do today. We can graph the y-intercept, 3.771. I'll put right here. I'll do this with a little blue X. 3.7 is going to be back here. So that's my y-intercept. Okay. Then don't forget, so that's 1 point, and then you need another point. You can get the mean point. So back to the beginning, the mean point is always on the line, which is x bar, y bar. And to go back, I think x bar was 5. Yeah, that's easy. And y bar was 8.25. Okay, so you just graph that. 5, 8.25 is going to be about here, I think. Remember, the mean point is always on the line. Okay, now this is easy. Just touch the y-intercept and draw through the mean point, and there's a line of best fit. Okay. And that's it for chapter 3. So as far as homework goes, get yourself through chapter 3, where you're going to be computing R and interpreting R and computing equations of lines of best fit and also making some predictions with it. So the idea with predictions is, you know, predict a murder rate for a city with X equals, I'm going to say 6, which means 6,000 automatic weapons. Got it? That seems like so many. Okay, so I would just do y hat equals the slope times x plus the y-intercept. Okay, so the slope was 0.8958. X I'm choosing to be 6. I just got a hypothetical city with 6,000 automatic weapons. Okay, plus the y-intercept, which was 3.771. Okay, so run the numbers. 0.8958 times 6,000, which is just represented as a 6, plus 3.771. Oops, 771, right? Yeah. So, oops, I did it wrong again. Hang on. Okay, anybody get that? I know it's time to go. Let's just get this one thing. 9.14, yeah, let's just round it to a 9.14. That's approximate one. X, this is murders per 100,000 people that are predicted. So these are, again, we don't have, this is not a real city, but for it, we're predicting 9.14, you know, murders per 100,000. Is that absolute? No, absolutely not. It's not absolute. Is it going to be a pretty good prediction? Yeah, it's going to be pretty good because the relationship is strong between these two variables. Will it be exactly right? No, absolutely not. So there will be some margin for error in a prediction like this. And there are formulas for the margin of error for this, but it's more complicated than we're going to do. So thanks for hanging in, everybody. And I will be sending you information today and possibly over the weekend about your test on Friday. But it's just going to cover the material in 7, 8, and 9. Mostly just confidence intervals and hypothesis tests. So there's 2 or 3 confidence intervals and a handful of hypothesis tests. Okay, and it'll be done on Canvas. So keep an eye open for your email. Take care, everybody. I'll start my office hour in just a few minutes. And you guys have a good day too.